This is the last section in chapter 4 that we are going to go through. There is one more section, 4.9, which is antiderivatives. However, I think that's best suited for as an introduction to chapter 5. So we're not going to do 4.9 for this test. We're going to save it for after the test. So Newton's method is the last thing we're going to go through. Now, let me tell you what Newton's method is used for. Newton's method is a good way to find zeros of a function. Okay, it's a numerical method to find the zeros, and since it's a numerical method, it means it's just easily programmable. If you use the zero feature on your calculator, as in you plug in a equation into your y equals, and then hit second trace and go to the zero option, I believe it's like option number 2, it will help you locate the zeros based on like a left bound, right bound, and then a guess, okay? Now, we don't have to do a left bound or right bound here. Let's go ahead and talk through the method and show you exactly what it's doing. Now, Newton's method requires the equation of the tangent line, okay? So if we have some function f of x in point slope form, remember this is point slope form, we could write the equation of the tangent line in point slope form using f of x's, okay? Now, let's say we want to write the equation of the tangent line for our function at x is equal to x1. Normally, we write at x equals a, and a is some number. We're going to write x1. There's a reason for it, and we'll see it in a little bit, okay? So now, also, y1 is going to be equal to f of x1, and then, of course, our slope is the derivative at our point x1. So let me go ahead and rewrite this equation using our definitions over here. So this is actually y is equal to f of x. So f of x is equal, or not equal to, minus f of x1, which is equal to my slope, which is the derivative at x1 times x minus x1. So this is the equation of the tangent line to whatever function this is at the point x1. Alright? Now, what we're going to do is we're going to plug in this point right here. So plug in x2 comma 0. x2 comma 0. That means for the x right here, I'm going to plug in x2. For the f of x right here, I'm going to plug in 0. Now let me explain why we're doing that and how Newton's method is going to work. I'm going to draw you a picture. So, say I have some function, right? It doesn't matter what the function is. As you can see, it has a 0 right there, it has a 0 right there, and it has a 0 right there, okay? Now let's go ahead and apply Newton's method, and let's see what it's going to do. We need the equation of the tangent line at some point x1, whatever that point may be. Now I'm just going to randomly pick a point. Let's say right there is x1. And now let me go ahead and draw the tangent line to it. So there's the tangent line, okay? Now, here's what Newton's method is doing. You start at an x1, and then what we're going to do at some x2, we don't know what this x2 is, the line is going to equal 0, okay? So that means we're just finding the x-intercept of this line, which happens to be right here. Okay, so this would represent x2. And now what we do is we find another tangent line. Now, how I drew my graph, I ended up being a horizontal tangent. That's just because I generically drew it. Let's see. Let me see if I can fix this. Something like that. There we go. That's a little better. Now it's not landing at a minimum. Okay? Now, if I were to choose this point and draw this tangent line, like that, I'm going to find a new point, which is x3. Or, sorry, not x. Oh, yeah, x3 right here. It's the 0 of this line. And then I'm going to go up to the function. I'm going to repeat the process. And it's going to land on 0 there. I'm going to get a new point. And what you are doing is you keep finding the 0 of the tangent line. And then you keep making these tangents. And eventually, this point will get closer and closer to one of these zeros. Okay? It's an iterative method. You have to do these iterations over and over and over and over. And eventually, the tangent lines, the zeros of the tangent lines, will eventually get closer and closer to the zeros of the actual function. Now, it's really hard to draw a nice picture of this by freehand. If you look in the book, actually, give me a second, I'll be able to tell you. There is a nice picture of it, somewhere in the book, of how this actually works. Yeah, if you look on page 346, it draws a lot better picture of this over on the left-hand side of that page, okay? But that's the idea of what we're doing. We're using the tangent line to approximate the zeros of the actual function, and we do multiple tangent lines at these new x values to obtain the tangent line. Or sorry, to obtain the zeros, to attain the roots. Okay, so now let's see what happens when we plug in x2 and plug in 0 into here. So remember, 0 is going in for f of x, x2 is going in for the x's. So 0 minus f of x1 is equal to f prime of x1 times x2 minus x1. Now, I'm going to solve for x2. That means I got to divide both sides by f prime of x1. F prime of x1. 0 goes away. I get negative f of x1 divided by f prime of x1 is equal to x2 minus x1. If I solve for x2, I get x2 is equal to x1 minus f of x1 divided by f prime of x1. So what this is doing is that this is my first approximation where I think the 0 is. I compute this number right here. I take the function evaluated at f of x, or at x1. I take the derivative evaluated at x1, and then I subtract the two, okay? And that gives me my new x value. I'm going to take this answer. It's going to become my x1. I'm going to plug in these two, so it's an iterative process. I'm going to keep that there. We don't need anything else but that. Oops. Didn't mean to erase that x2. So let's write it up here. x2 is equal to x1 minus f of x1 divided by f prime of x1. So this is the first iteration. So then, to get the next iteration, x3, That's going to be x2 minus f of x2 divided by f prime of x2. This is the second iteration. Now you just repeat the process. x4 is equal to x3 minus f of x3 divided by f prime of x3. And you just keep doing this until these numbers converge onto a single number, okay? Again, every time you do an iteration, these x values should get closer and closer to an actual zero of the function, okay? You could write this a little more general, as I do have it in my notes. It says x sub n plus 1 is equal to xn minus f of xn divided by f prime of xn, where n is just how many iterations are you doing, okay? So if I plug in 1 everywhere, that means this is a 2. That's the first iteration. If I plug in 2 everywhere, all of these are 2, just like all of these are 2, and this one would be 3. That'd be the second iteration. So n here stands for what iteration are you up to, okay? So again, this is just an iterative process. You repeat this same formula over and over and over until this number converges onto a single value. Now, there is a note that says if Newton's method fails to converge or fails to be a better approximation than your previous guess, then what you might have to do is choose a different starting point. Sometimes if you choose a starting point too far from a zero or too close to a where a horizontal tangent is, like think about the derivative. The derivative is the slope. If you are near a minimum or a maximum, the slope is going to be 0. So this is going to be some number divided by 0. You're not going to be able to do it. So if you're close to a horizontal tangent, close to discontinuities, close to sharp points, or really your initial guess is really far away from one of the zeros, as you do this iterative process, it may not be getting closer and closer to the actual zero. Sometimes it blows up to infinity, sometimes you get 0, sometimes it just keeps randomly bouncing back and forth between values and it doesn't go anywhere, okay? All that means is you need to pick a different number. You need to start somewhere else and do the process over again. Now, in these examples, I am going to show you, first, we're going to do one example by hand, and then I'll show you how to speed it up using the calculator. So in the next videos, when I go through these examples, have your calculator ready. I will show you the commands on how to do this, and I'm perfectly fine with you using your calculator on the test to compute these iterations, how I'm showing you right here, okay? What I'd want you to do, though, is at least write down what your x2s and x3s are going along the way, okay? And I'll show you what I mean when we go through it.